Good afternoon, everyone. Today I'm presenting my analysis on predicting job change intentions using machine learning techniques. This work addresses a critical HR challenge, identifying which candidates are likely to stay with the company long term versus those who will seek new opportunities shortly after hiring. My name is Atkinson, and shortly over the next 10 minutes, I'll walk you through our methodology, results, and the actionable insights we've uncovered. Let's start with the context. Imagine you're running HR for a large data science company that invests heavily in training programs. You're spending significant resources, both time and money, on recruitment and onboarding. But here's the challenge. What if the candidates you hire leave just after the first few months? The cost of a bad hire is substantial. Research shows it can reach $50,000 or more when you factor in recruitment costs, training investments, and lost productivity during the transition period. For a company hiring hundreds of candidates annually, this adds up quickly. So the question becomes, can we predict which candidates will stay versus which ones are likely to leave? If we can identify retention risks early, we can make smarter hiring decisions, tailor our retention strategies, and ultimately save significant costs. That's exactly what we set out to do with this analysis. For this project, we worked with a dataset of over 11,000 candidates who completed data science courses, specifically 11,494 training samples where we know whether they changed jobs or stayed. The dataset contains 72 features spanning 5 categories. We have geographic information, including 60 city indicators and a city development index. We have demographic data, like gender and experience status. Educational features further capture their qualification level, discipline, and university enrollment, while professional attributes include years of experience, current company size, and type. And finally, we tracked engagement through training hours completed. Given all this, our task was to build a model on this historical data, then apply it to predict outcomes for an additional 3,832 unlabeled candidates. Here's where things get interesting and challenging. When we examined our target variable, we discovered significant class imbalance. As you can see on this chart, 75.5% of candidates did not change jobs, while only 24.5% did change jobs. That's roughly a 3-to-1 ratio favoring the no change class. So why does this matter? Well, if we built a naive model that simply predicted no job change for everyone, we'd achieve a 75% accuracy. Sounds great on paper, right? But it would be completely useless because we miss every single candidate who actually intended to leave, which is precisely what HR needs to identify. So we couldn't rely on standard training approaches. Instead, we employed a technique called SMOTE, Synthetic Minority Oversampling Technique. This creates synthetic examples of the minority class by interpolating between existing instances. As shown in the before and after comparison, we balanced our training data to a 50-50 distribution, expanding from about 9,200 samples to nearly 14,000. Now onto the methodology. Let me walk you through our systematic approach, which consisted of 4 key steps. First, data pre-processing. Not all categorical variables are created equal. Some have natural ordering, like experience ranging from less than 1 year to over 20 years, whilst others don't, like gender or academic discipline. We applied ordinal encoding to preserve these natural relationships and one-hot encoding for nominal categories. We also standardized numerical features to ensure fair treatment across different scales. Second, we handled the class imbalance using SMOTE, as I just described, balancing our training data whilst keeping the test set untouched for fair evaluation. Third, model development. We didn't just build one model and call it a day. We systematically compared 3 different classified families consisting of logistic regression as a linear baseline, random forest as an ensemble method, and gradient boosting for sequential learning. For each, we used grid search CV with 5 cross-fold validation, testing 168 unique hyperparameter combinations across 840 total model fits to find optimal configurations. Finally, evaluation. We assessed all models on a held-out test set of 2,299 candidates using F1 score as our primary metric, which balances precision and recall, both critical for HR decision-making. So how did our models actually perform? As you can see from this chart, gradient boosting emerged as a clear winner, with an F1 score of 0.5564. Logistic regression then came second at 0.5298, closely followed by random forest at 0.5217. Now let's interpret what this F1 score actually means in practical terms. Our best model achieved a precision of 56%, meaning when we predict a candidate will change jobs, we're correct about 56% of the time. We also achieved a recall of 55%, meaning we successfully identified 55% of candidates who actually do change jobs. And importantly, we maintained 78% overall accuracy on the held out test set. So why did gradient boosting win? Its sequential learning approach allows later trees to correct mistakes made by the earlier ones, creating a more refined decision boundary than random forest independent trees. It also balanced precision and recall better than logistic regression. This performance is quite solid given the inherent unpredictability of human career decisions and the limitations available in our features. Now that we've built a strong model, the next question is, what actually drives these predictions? Looking at this horizontal bar chart, we can see the top features ranked by their contribution to the model. Number 1, City Development Index, accounts for 28.5% of predictive power. This was by far the strongest predictor, with nearly double the second place feature. Second on the list is company size, with 15.7% importance. This tells us organizational context profoundly shapes career decisions. Next up is years of experience, with 11.5% importance. This makes sense given the more invested you are in a company, the less likely you are to actually move on. Further, job change redundancy shows 8.7% importance. This further builds upon the previous factor's temporal dimension and adds valuable context. Lastly, training hours stated a 7.8% importance, which implies that the time candidates invested in the course completion is telling. Based on these findings, we can offer concrete recommendations for HR strategy. First, geography matters most. Candidates from high development cities need competitive offers, and as such, you should look to tailor recruitment budgets by city development level. Secondly, assess company size context carefully. Candidates from small companies seeking opportunities at your larger firm may view you as a growth stepping stone. Conversely, large company candidates seeking smaller environments may desire a different culture. Screen for genuine organizational fit, not just skills. Third, implement career stage specific strategies. For juniors, emphasize growth opportunities and mentorship. For mid-level professionals, highlight leadership potential and project ownership. While for seniors, focus on autonomy, strategic roles, and work-life balance. Fourth, consider job change patterns. Candidates who change jobs recently versus those stable for 4+ years have different risk profiles. Discuss career stability and long-term goals during interviews. And here's the business impact. Our model identifies 55% of potential job changes, enabling more focused recruitment. If we conservatively estimate, this prevents just 50 bad hires annually at $50,000 each. We're looking at $2.5 million in annual savings. That's significant return on investment from a data science project. Let me wrap up with our key achievements and the value this brings. We successfully built a robust predictive model, achieving an F1 score of 0.5564 through rigorous methodology and extensive hyperparameter training. We identified the key drivers of job change decisions, and we delivered concrete recommendations that HR can implement immediately. Further, the business value is threefold, including data-driven screening, substantial cost savings, as well as strategic focus for HR. Though it's important to note that our model should serve as a decision support tool, not a replacement for human judgment. It provides one input alongside interviews, references, and assessments. Before I close, let me briefly touch on limitations and future work. Our F1 score represents moderate predictive power, which honestly reflects the inherent unpredictability of career decisions. We also lack some potentially valuable features like salary satisfaction, detailed job satisfaction metrics, or specific technical skills. Looking forward, several improvements could boost performance, including threshold optimization might add another percentage point, while feature engineering through interaction terms and polynomial features could capture nonlinear relationships. And critically, Regular retraining on fresh data will maintain model relevance as labour markets evolve. Thank you for your time.